All right, so we're going to continue our discussion on forward Euler method or explicit Euler method. So I was talking about one example here, which was a differential equation with three unknowns. That's basically this function on page 121 of the lecture notes. And we try to solve this using forward difference or forward Euler. So I showed the script. I'd like to run the script and show you what we get. So I just run the code. Alright, so now you see a subplot corresponds to this subplot function. So it says that split the plot area into 2 by 2 sub-areas. So this is a 2 by 2, right? So this is, 2 rows and 2 columns. So it's a 2 by 2 matrix. In each of them, we actually plot one of the y's. So this is basically y1, as you see here. Let me just maximize this. So you see y1, y2, y3, and actually these are really small. Let me just even increase the font. So that's about the label. So I'm going to make it 16 font. So let's make everything 16. Stop it and rerun it. Yes, a bigger font. So now here is x, right? So all of the x-axis is x, and then here's the y1, y2, y3. So it shows the solution for all three y1 using for every pair of x and y, you have a dot here. So that means there are 100 dots along the line as we initially set, right? So there's 100 lines here. 100 points here. Okay. So again, the way to solve a differential equation is using the iterations. And for every iteration, we find the next y value or the y value of the next x point based on the y value of the current. Right, so this is the next y is equal to the current y plus delta x times the function f, which is a function of all the current values x and y. Okay, and this f is given. F is basically the right-hand side of a differential equation according to the definition right here. So this f is known. We're looking for y vector. Okay, so there's a problem actually with forward Euler method, and that is the error actually is on the order of first order. So in the lecture notes, I actually indicated this by order del x, which means the error that we get from solving differential equation using this approach is on the order of first, or the order of 1. Okay, so that means if I increase, or let's say if I decrease my delta x by a factor of 10, right, my error in the solution in the y is going to go by a factor of 10. It's linear with respect to delta x. If I lower my delta x by maybe a factor of 100, then my error in y value is going to go by a factor of 100. It's going to go down by a factor of 100. So it's linear in x. Now, there are more accurate methods that actually goes with second order in delta x, which means if you lower the delta x by a factor of 10, then the error goes down by a factor of 100. It's like 10 to the second power. And so lowering delta x by a factor of 10 means that if I use right now, let's say 100 points along the x-axis, okay, I can go ahead and instead use 1,000 points along the same x-axis. So 1,000 points compared to 100 points, and that lowers my interval by a factor of 10. The distance between every two successive x values is going to go down by a factor of 10 using 1,000 points as opposed to 100 points. Okay, so that's what I mean by lowering delta x by a factor of 10, which means we are using 10 more points or 10 times more points along the x-axis when we solve differential equations. One thing I'd like to note that in the numerical solution of differential equations, we always solve for the y value at the discrete x values. So that means we only look for the y values at those x points. We cannot solve y value for every x, right? So we just discretize our x to some discrete points and then solve the solution, or solve for the solution only at those discrete points. Now, by increasing the number of discrete points, we lower delta x. So that's what I mean by lowering delta x. Okay, so the second method we're going to look at is Runge-Kutta method. Now, this method is of second order, which means if you lower then delta x by a factor of 10, the error goes down by a factor of 100. So it actually is more accurate. It gets to the solution much quicker. Okay, so let's look at explicit Runge-Kutta method. It's called explicit because at the end of the day, when we discretize the equation in terms of yi and yi plus 1, the unknown, which is yi plus 1, only shows up on one side, pretty much like the forward Euler. So in forward Euler, yi plus 1 was on one side and everything else on the right side in terms of I. We have methods that actually I plus 1 variable shows up on both sides of the differential equation. So we're going to look at that hopefully maybe in the next video or so. Okay, so in explicit Runge-Kutta method, second order Runge-Kutta method, we find two intermediate variables called k1 and k2, where k1 is the function evaluated, this f, which is the right hand side of differential equation, evaluated at xi, yi, the current x and the current y. k2 is the same function f evaluated at xi plus delta x, right? And then yi plus delta x times k1. So basically, when I evaluate f at two different x and y values compared to k1, right? Now we have k1 and k2, we average them, times delta x is going to be what we add to the current y to get the next yi plus 1. So the algorithm is very well suited for scripting. We just calculate ky, k2, k1, k2, add them up, get, average them, divide by 2, and then times delta x plus the current y, we get the next one. So it's very straightforward. Let's look at how we can solve the same problem now, this time using second order RK2, or second order RK method, or RK2. So I'm going to move my breakpoints to the next approach, which we haven't talked about it yet. Now here, I'm just saying this is also called RK2. Okay, so I pretty much script exactly what I have in notes. First, we calculate k1, which is the function evaluated at the current point. My current point is xi minus 1 y plus 1I minus 1. And hope this is not confusing that I'm using I minus 1 here, but in the notes I used I on the right side. The difference is here in the script, my I starts from 2, which means I minus 1 starts from 1. Okay, that is true because I initially have x1 and y1, based on which I calculate y2. And this is basically just a matter of how I call the indices, nothing else. So this is pretty much identical to these three equations right here. Alright, so after we calculate k1, we're going to calculate k2 at xi plus del x and yi plus del x k1. And I do the same thing here. So I calculate k2 at xi minus 1 del x plus yi minus 1 plus del x k1. That's exactly what I had in the note. I get k1, k2, I average them out, and then times del x plus the current y, I get the next y. And then I crank up my x to be the current x plus delta x. Now I get ready for the next cycle. So we're going to iterate this, n minus 1 times until we get all the y values. So I think now we're ready to run the code. One more thing is that to plot the function, I use the same subplot. I use, the 3 panels of the subplot to plot y1, y2, y3. And the rest is identical to the forward Euler. You have the x limit, y limit, italicize the x label, y label. And I have to make them 16 so you guys can see it in a video. Let's do all of them 16 font. Alright, so let's stop it here. run it. So there you go. I actually went through all the steps in the RK2 method, and here's the solution. So now I'm over plotting on top of the solution from forward Euler. So forward Euler was blue. The red one is RK2. Now you see a little bit of error here. In fact, RK2 is more accurate. So this error is because RK2 is more accurate than forward Euler. So it captures the error actually toward the large x values. And as you go to larger and larger x values, the error actually accumulates. So you see that the error goes up as we go to higher x value. Okay, so, but more or less it's not that bad. It's close. I mean, it's close to the RK2. I mean, forward Euler is close to RK2. It's supposed to be. Not too much off, but I think it's okay. All right. So let me minimize this and go back to the script. Okay. So in the next part of this video, we're going to look at an even more accurate method, which is RK4. Now in RK4, which is actually fourth order, and the error actually goes down proportional to delta x to the fourth power, which means if I lower my delta x by a factor of 10, in other words, make the interval smaller by a factor of 10, then the error goes down by a factor of 10 to the 4, which means 10,000 times the error goes down. So it's very, very fast. So this method is actually it's more accurate than even RK2. And we said RK2 is more accurate than forward Euler. So let me go back to the lecture notes to basically look at the theory part of it, and then we come back and talk about the script in a minute. So in RK4, it's very similar to RK2. We calculate now this time 4 k values, k1, 2, 3, and 4, as opposed to only 2 k values for RK2. And the first 2 k values are very similar to RK2. K1 is the function evaluated at xi, yi. K2, you evaluate the function. This function actually is, again, this is the right side of my differential equation. Okay, so hopefully this is not confusing. Okay, we evaluated at xi, now half delta x, and then half delta x times k1 for y. Okay, this is going to be k2. For k3, we still do half del x plus ki plus xi, but on the yi side, we do half del x times k2. Okay, and this goes to the y value and gives us k3. Now k4 is we add just a complete delta x to xi, and then delta x times k3 we just calculated here. This is going to be the y component of f. Or now we have the 4 k values, we get the basically weighted average of them. So k1, 2k2, 2k3, k4, all of them divided by 6 times del x gives us yi plus 1. So pictorially, what we are doing here is, in the first equation right here, we approximate basically k1 by the slope of the function at the current x0 and y0. So this is the k1, the slope is k1. In this line, we are approximating the slope by the slope of the function, or the slope of tangent at this xy, so which means from x0 we go forward del x plus, or del x divided by 2, and then evaluate the slope right here, which is about the slope of this line. And you know that this does not necessarily come on the curve. If this is the exact solution, because of the error, this point is a little bit higher than the corresponding point on the curve. Fine. Now we go to k3. K3 is going to be at the same point, same x value, but at a different y value, and the y value actually is coming from y0 plus k2 times the x squared. So with this slope we get here, we actually start from the beginning and then go from here with that slope until we hit this x0 plus del x over 2, and whatever we hit, it's going to be the slope at which we calculate k3. Okay? And then k4 is going to be, well, we're going to now move from x0, complete del x step, and then at this point we calculate the slope. So now we have four slopes,